Learning objectives. In this chapter, the user will learn the following in detail. An introduction to the multidisciplinary field of data mining. Discussion on the evolutionary path of database technology that has led to the need for data warehousing and data mining. Different kind of data on which data mining is applied. Classification of data mining system. Major issues in data mining. Stress on importance of its application potential. Introduction. Why data mining is in high demand and how it is part of the natural evolution of information technology. Data mining with respect to the knowledge discovery process. About data mining from many aspects such as the kinds of data that can be mined, the kinds of knowledge to be mined, the kinds of technologies to be used, and targeted applications. A multi-dimensional view of data mining. Major data mining research and development issues. An introduction to the multidisciplinary field of data mining. Mining is a vivid term characterizing the process that finds a small set of precious nuggets from a great deal of raw material. Thus, such a misnomer carrying both data and mining became a popular choice. In addition, many other terms have a similar meaning to data mining. For example, knowledge mining from data, knowledge extraction, data pattern analysis, data archaeology, and data dredging. Many people treat data mining as a synonym for another popularly used term, knowledge discovery from data, or KDD, while others view data mining as merely an essential step in the process of knowledge discovery. Data mining is the process of discovering interesting patterns and knowledge from large amounts of data. The data sources can include databases, data warehouse, the web, other information repositories, or data that are streamed into the system dynamically. Data mining as a step in the process of knowledge discovery. The knowledge discovery process is an iterative sequence of the following steps. 1. Data cleaning, to remove noise and inconsistent data. 2. Data integration, where multiple data sources may be combined. 3. Data selection, where data relevant to the analysis task are retrieved from the database. 4. Data transformation, where data are transformed and consolidated into forms appropriate for mining by performing summary or aggregation operations. 5. Data mining, an essential process where intelligent methods are applied to extract data patterns. 6. Pattern evaluation, to identify the truly interesting patterns representing knowledge based on interestingness measures. 7. Knowledge presentation, where visualization and knowledge representation techniques are used to present mined knowledge to users. Classification of data mining system. There are a number of data mining functionalities. These include characterization and discrimination, the mining of frequent patterns, associations and correlations, classification and regression, clustering analysis, and outlier analysis. Data mining functionalities are used to specify the kinds of patterns to be found in data mining tasks. In general, such tasks can be classified into two categories: descriptive and predictive. Descriptive mining tasks characterize properties of the data in a target dataset. Predictive mining tasks perform induction on the current data in order to make predictions. Class, concept description, characterization, and discrimination. Data entries can be associated with classes or concepts. For example, in the all-electronics store, classes of items for sale include computers and printers, and concepts of customers include big spenders and budget spenders. It can be useful to describe individual classes and concepts in summarized, concise, and yet precise terms. Such descriptions of a class or concept are called class concept descriptions. These descriptions can be derived using data characterization by summarizing the data of the class under study, often called the target class in general terms, or data discrimination by comparison of the target class with one or a set of comparative classes, often called the contrasting classes, or both data characterization and discrimination. Data characterization is a summarization of a general characteristics or features of a target class of data. The data corresponding to the user-specified class are typically collected by a query. For example, to study the characteristics of software products with sales that increased by 10% in the previous year, the data related to such products can be collected by executing an SQL query on the sales database. There are several methods for effective data summarization and characterization. The data cube-based OLAP roll-up operation can be used to perform user-controlled data summarization along a specified dimension. An attribute-oriented induction technique can be used to perform data generalization and characterization without step-by-step user interaction. The output of data characterization can be presented in various forms. Example includes pie charts, bar charts, curves, multidimensional data cubes, and multidimensional tables, including crosstabs. The resulting descriptions can also be presented as generalized relations or in rule form, called characteristic rules. Data discrimination is a comparison of the general features of the target class data objects against the general features of objects from one or multiple contrasting classes. The target and contrasting classes can be specified by a user, and the corresponding data objects can be retrieved through database queries. For example, a user may want to compare the general features of software products with sales that increased by 10% last year against those with sales that decreased by at least 30% during the same period. The methods used for data discrimination are similar to those used for data characterization. The forms of output presentation are similar to those for characteristic descriptions, although discrimination descriptions should include comparative measures that help to distinguish between the target and contrasting classes. Discrimination descriptions expressed in the form of rules are referred to as discriminant rules. Mining frequent patterns, associations, and correlations. Frequent patterns, as the name suggests, are patterns that occur frequently in data. There are many kinds of frequent patterns, including frequent item sets, frequent subsequences, also known as sequential patterns, and frequent substructures. A frequent item set typically refers to a set of items that often appear together in a transactional dataset. For example, milk and bread, which are frequently bought together in grocery stores by many customers. A frequently occurring subsequence, such as the pattern that customers tend to purchase first a laptop followed by a digital camera and then a memory card, is a frequent sequential pattern. A substructure can refer to different structural forms, for example, graphs, trees, or lattices that may be combined with item sets or subsequences. If a substructure occurs frequently, it is called a frequent structured pattern. Mining frequent patterns leads to the discovery of interesting associations and correlations within data. Note that this is an association involving more than one attribute or predicate, for example, age, income, and buys. Adopting the terminology used in multidimensional databases, where each attribute is referred to as a dimension, the above rule can be referred to as a multidimensional association rule. Typically, association rules are discarded as uninteresting if they do not satisfy both a minimum support threshold and a minimum confidence threshold. Additional analysis can be performed to uncover interesting statistical correlations between associated attribute value pairs. Frequent item set mining is a fundamental form of frequent pattern mining. Classification and regression for predictive analysis. Classification is the process of finding a model or function that describes and distinguishes data classes or concepts. The models are derived based on the analysis of a set of training data, that is, data objects for which the class label is unknown. The derived model may be represented in various forms such as classification rules, if-then rules, decision trees, mathematical formulae, or neural networks. A decision tree is a flow chart-like tree structure where each node denotes a test on an attribute value, each branch represents an outcome of the test, and tree leaves represent classes or class distributions. They can easily be converted to classification rules. A neural network, when used for classification, is typically a collection of neuron-like processing units with weighted connections between the units. There are many other methods for constructing classification models, such as native Bayesian classification, support vector machines, and nearest neighbor classification. Whereas classification predicts categorical, discrete, unordered labels, regression models continuous valued functions. That is, regression is used to predict missing or unavailable numerical data values rather than discrete class labels. The term prediction refers to both numeric prediction and class label prediction. Regression analysis is a statistical methodology that is most often used for numeric prediction, although other methods exist as well. Regression also encompasses the identification of distribution trends based on the available data. Classification and regression may need to be preceded by relevance analysis, which attempts to identify attributes that are significantly relevant to the classification and regression process. Such attributes will be selected for the classification and regression process. Other attributes which are irrelevant can then be excluded from consideration. Cluster analysis. Unlike classification and regression, which analyze class-labeled training datasets, clustering analyzes data objects without consulting class labels. In many cases, class-labeled data may simply not exist at the beginning. Clustering can be used to generate class labels for a group of data. The objects are clustered or grouped based on the principle of maximizing the intra-class similarity and minimizing the inter-class similarity. That is, clusters of objects are formed so that objects within a cluster have high similarity in comparison to one another, but are rather dissimilar to objects in other clusters. Each cluster so formed can be viewed as a class of objects from which rules can be derived. Clustering can also facilitate taxonomy formation, that is, the organization of observations into a hierarchy of classes that group similar events together. Figure shows a 2D plot of customer data with respect to customer locations in a city, showing 3 data clusters. Outlier analysis. A data set may contain objects that do not comply with the general behavior or model of the data. These data objects are outliers. Many data mining methods discard outliers as noise or exceptions. However, in some applications, such as fraud detection, the rare events can be more interesting than the more regularly occurring ones. The analysis of outlier data is referred to as outlier analysis or anomaly mining. Outliers may be detected using statistical tests that assume a distribution or probability model for the data, or using distance measures where objects that are remote from any other cluster are considered outliers. Rather than using statistical or distance measures, density-based methods may identify outliers in a local region, although they look normal from a global statistical distribution view. Different kind of data on which data mining is applied. As a general technology, data mining can be applied to any kind of data as long as the data are meaningful for a target application. The most basic forms of data for mining applications are database data, data warehouse data, and transactional data. Data mining can also be applied to other forms of data, for example, data streams, ordered sequence data, graph or network data, spatial data, text data, multimedia data, and the WWW. Data mining will certainly continue to embrace new data types as they emerge. Database data. A database system, also called Database Management System, DBMS, consists of a collection of interrelated data, known as a database, and a set of software programs to manage and access the data. The software programs provide mechanisms for defining database structures and data storage, for specifying and managing concurrent, shared, or distributed data access, and for ensuring consistency and security of the information stored, despite system crashes or attempts at unauthorized access. A relational database is a collection of tables, each of which is assigned a unique name. Each table consists of a set of attributes, columns of fields, and usually stores a large set of tuples, records, or rows. Each tuple in a relational table represents an object identified by a unique key and described by a set of attribute values. A semantic data model, such as an entity relationship (ER) data model, is often constructed for relational databases. It represents the database as a set of entities and their relationships. The fictitious all-electronic store is used to illustrate concepts throughout this video. The company is described by the following relation tables: customer, item, employee, and branch. The headers of these tables described here are shown in the following figure. A header is also called the schema of a relation. The relation customer consists of a set of attributes describing the customer information, including a unique customer identity number, customer ID, customer name, address, age, occupation, annual income, credit information, and category. Similarly, each of the relations item, employee, and branch consists of a set of attributes describing the properties of these entities. Tables can also be used to represent the relationships between or among multiple entities. In our example, these include purchases. Customer purchases item, creating a sales transaction handled by an employee. Item sold lists items sold in a given transaction, and works at, employee works at a branch of all electronics. Relational data can be accessed by database queries written in a relational query language, example SQL, or with the assistance of graphical user interfaces. A given query is transformed into a set of relational operations such as join, selection, and projection, and is then optimized for efficient processing. A query allows retrieval of specified subsets of the data. Suppose that your job is to analyze the all-electronics data. Through the use of relational queries, you can ask things like, show me a list of all items that were sold in the last quarter. Relational languages also use aggregate functions such as sum, average, count, maximum, and minimum. Using aggregates allows you to ask, show me the total sales of the last month, grouped by branch, or how many sales transactions occurred in the month of December, or which salesperson had the highest sales. When mining relational databases, we can go further by searching for trends or data patterns. For example, data mining systems can analyze customer data to predict the credit risk of new customers based on their income, age, and previous credit information. Data mining systems may also detect deviations, that is, items with sales that are far from those expected in comparison with the previous year. Such deviations can then be further investigated. For example, data mining may discover that there has been a change in packaging of an item or a significant increase in price. Relational databases are one of the most commonly available and richest information repositories, and thus they are a major data form in the study of data mining. Data warehouses. Suppose that All Electronics is a successful international company with branches around the world. Each branch has its own set of databases. The president of Electronics has asked you to provide an analysis of the company's sales per item type per branch for the third quarter. This is a difficult task, particularly since the relevant data are spread out over several databases physically located at numerous sites. If All Electronics had a data warehouse, this task would be easy. A data warehouse is a repository of information collected from multiple sources, stored under a unified schema, and usually residing at a single site. Data warehouses are constructed via a process of data cleaning, data integration, data transformation, data loading, and periodic data refreshing. Following figure shows a typical framework for construction and use of data warehouse for All Electronics. To facilitate decision-making, the data in the data warehouse are organized around major subjects, that is, customer, item, supplier, and activity. The data are stored to provide information from a historical perspective, such as in the past 6 to 12 months, and are typically summarized. For example, rather than storing the details of each sales transaction, the data warehouse may store a summary of the transactions per item type for each store or summarized to a higher level for each sales region. A data warehouse is usually modeled by a multi-dimensional data structure called a data cube, in which each dimension corresponds to an attribute or a set of attributes in the schema, and each cell stores the value of some aggregate measure such as count or sum, sales amount. A data cube provides a multi-dimensional view of data and allows the pre-computation and fast access of summarized data. Figure shows a typical framework of a data warehouse for all electronics. By providing multi-dimensional data views and the pre-computation of summarized data, data warehouse systems can provide inherent support for OLAP. Online analytical processing operations make use of background knowledge regarding the domain of the data being studied to allow the presentation of data at different levels of abstraction. Such operations accommodate different user viewpoints. Examples of OLAP operations include drill down and roll up, which allow the user to view the data at different degrees of summarization as illustrated in the figure. For instance, we can drill down on sales data summarized by quarter to see data summarized by month. Similarly, we can roll up on sales data summarized by city to view data summarized by country. Although data warehouse tools help support data analysis, additional tools for data mining are often used for in-depth analysis. Multidimensional data mining, also called exploratory multidimensional data mining, performs data mining in a multidimensional space in an OLAP style. That is, it allows the exploration of multiple combinations of dimensions at varying levels of granularity in data mining, and thus has greater potential for discovering interesting patterns representing knowledge. Transactional data. In general, each record in a transactional database captures a transaction, such as customer's purchase, a flight booking, or a user's clicks on a web page. A transaction typically includes a unique transaction identity number, trans ID, and a list of the items making up the transaction, such as the items purchased in the transaction. A transactional database may have additional tables which contain other information related to the transaction, such as item description, information about the salesperson or the branch, and so on. As an analyst of all electronics, you may ask, which items sold well together? This kind of market basket data analysis would enable you to bundle groups of items together as a strategy for boosting sales. For example, given the knowledge that printers are commonly purchased together with computers, you could offer certain printers at a steep discount, or even for free, to customers buying selected computers in the hope of selling more computers, which are often more expensive than printers. A traditional database system is not able to perform market basket data analysis. Fortunately, data mining or transactional data can do so by mining frequent item sets, that is, sets of items that are frequently sold together. Figure shows a fragment of a transactional database for sales at all electronics. Other kinds of data. Besides relational database data, data warehouse data, and transaction data, there are many other kinds of data that have versatile forms and structures and rather different semantic meanings. Such kinds of data can be seen in many applications: time-related or sequence data, historical records, stock exchange data, and time series and biological sequence data. Data streams, example, video surveillance and sensor data, which are continuously transmitted. Spatial data, example, maps. Engineering design data, example, the design of buildings, system components, or integrated circuits. Hypertext and multimedia data, including text, image, video, and audio data. Graph and network data, example, social and information networks, and the web, a huge widely distributed information repository made available by the Internet. These applications bring about new challenges like how to handle data carrying a special structure, for example, sequences, trees, graphs, and networks, and specific semantics such as ordering, image, audio, and video contents, and connectivity, and how to mine patterns that carry rich structures and semantics. Various kinds of knowledge can be mined from these kinds of data. Here we list just a few. Regarding temporal data, for instance, we can mine banking data for changing trends, which may aid in the scheduling of bank tellers according to the volume of customer traffic. Stock exchange data can be mined to uncover trends that could help you plan investment strategies. For example, the best time to purchase all electronic stock. We could mine computer network data streams to detect intrusions based on the anomaly of message flows, which may be discovered by clustering, dynamic construction of stream models, or by comparing the current frequent patterns with those at a previous time. With spatial data, we may look for patterns that describe changes in metropolitan poverty rates based on city distances from major highways. The relationships among a set of spatial objects can be examined in order to discover which subsets of objects are spatially autocorrelated or associated. By mining text data, such as literature on data mining from the past 10 years, we can identify the evolution of hot topics in the field. By mining user comments on products, which are often submitted as short text messages, we can access customer sentiments and understand how well a product is embraced by a market. From multimedia data, we can mine images to identify objects and classify them by assigning semantic labels or tags. By mining video data of a hockey game, we can detect video sequences corresponding to goals. Web mining can help us learn about the distribution of information on the WWW in general, characterize and classify web pages, and uncover web dynamics and the association and other relationships among different web pages, users, communities, and web-based activities. It is important to keep in mind that in many applications, multiple types of data are present. For example, in web mining, there often exists text data and multimedia data, such as pictures and videos, on web pages, graph data like web graphs, and map data on some websites. In bioinformatics, genomic sequences, biological networks, and 3D spatial structures of genomes may coexist for certain biological objects. Mining multiple data sources of complex data often leads to fruitful findings due to the mutual enhancement and consolidation of such multiple sources. On the other hand, it is also challenging because of the difficulties in data cleaning and data integration, as well as the complex interactions among the multiple sources of such data. While such data requires sophisticated facilities for efficient storage, retrieval, and updating, they also provide the fertile ground and raise challenging research and implementation issues for data mining. Discussion on the evolutionary path of database technology that has led to the need for data warehousing and data mining. Data mining can be viewed as a result of the natural evolution of information technology. The database and data management industry evolved in the development of several critical functionalities: data collection and database creation, data management, including data storage and retrieval and database transaction processing, and advanced data analysis, involving data warehousing and data mining. The early development of data collection and database creation mechanisms served as a prerequisite for the later development of effective mechanisms for data storage and retrieval, as well as query and transaction processing. Nowadays, numerous database systems offer query and transaction processing as common practice. Advanced data analysis has naturally become the next step. In addition, users gained convenient and flexible data access through query languages, user interfaces, query optimization, and transaction management. Efficient methods for online transaction processing, OLTP, where a query is viewed as a read-only transaction, contributed substantially to the evolution and wide acceptance of relational technology as a major tool for efficient storage, retrieval, and management of large amounts of data. After the establishment of database management systems, database technology moved toward the development of advanced database systems, data warehousing, and data mining for advanced data analysis and web-based databases. These systems incorporate new and powerful data models such as extended relational, object-oriented, object-relational, and deductive models. Application-oriented database systems have flourished, including spatial, temporal, multimedia, active, stream, and sensor, scientific and engineering databases, knowledge bases, and office information bases. Issues related to the distribution and diversification and sharing of data have been studied extensively. The steady and dazzling process of computer hardware technology in the past 3 decades led to large supplies of powerful and affordable computers, data collection equipment, and storage media. Data can now be stored in many different kinds of databases and information repositories. One emerging data repository architecture is a data warehouse. This is a repository of multiple heterogeneous data sources organized under a unified schema at a single site to facilitate management decision-making. Data warehouse technology includes data cleaning, data integration, and online analytical processing (OLAP), that is, analysis techniques with functionalities such as summarization, consolidation, and aggregation, as well as the ability to view information from different angles. Although OLAP tools support multidimensional analysis and decision-making, additional data analysis tools are required for in-depth analysis. For example, data mining tools that provide data classification, clustering, outlier anomaly detection, and the characterization of changes in data over time. Huge volumes of data have been accumulated beyond databases and data warehouses. The effective and efficient analysis of data from such different forms of data by integration of information retrieval, data mining, and information network analysis technologies is a challenging task. In summary, the abundance of data, coupled with the need for powerful data analysis tools, has been described as a data-rich but information-poor situation. The fast-growing tremendous amount of data collected and stored in large and numerous data repositories has far exceeded our human ability for comprehension without powerful tools. As a result, data collected in large data repositories became data tombs, data archives that are seldom visited. Consequently, important decisions are often made based not on the information-rich data stored in data repositories, but rather on a decision-maker's intuition, simply because the decision-maker does not have the tools to extract the valuable knowledge embedded in the vast amounts of data. Efforts have been made to develop expert system and knowledge-based technologies, which typically rely on users or domain experts to manually input knowledge into knowledge bases. Unfortunately, however, the manual knowledge input procedure is prone to biases and errors and is extremely costly and time-consuming. The widening gap between data information calls for the system development of data mining tools that can turn data tombs into golden nuggets of knowledge. Figure shows the evolution of database system technology over a period of time. The figure shows a world that is data-rich but information-poor. Major issues in data mining. We briefly outlined the major issues in data mining research, partitioning them into 5 groups: mining methodology, user interaction, efficiency and scalability, diversity of data types, and data mining and society. Many of these issues have been addressed in recent data mining research and development to a certain extent and are now considered data mining requirements. Others are still at the research stage. The issues continue to stimulate further investigation and improvement in data mining. Mining methodology. Researchers have been vigorously developing new data mining methodologies. This involves the investigation of new kinds of knowledge, mining in multidimensional space, integrating methods from other disciplines, and the consideration of semantic ties among data objects. In addition, mining methodologies should consider issues such as data uncertainty, noise, and incompleteness. Some mining methods explore how user-specified measures can be used to assess the interestingness of discovered patterns as well as to guide the discovery process. Let's have a look at these various aspects of mining methodology. Mining various and new kinds of knowledge. Data mining covers a wide spectrum of data analysis and knowledge discovery tasks, from data characterization and discrimination to association and correlation analysis, classification, regression, clustering, outlier analysis, sequence analysis, and trend and evolution analysis. These tasks may use the same database in different ways and require the development of numerous data mining techniques. Due to the diversity of applications, new mining tasks continue to emerge, making data mining a dynamic and fast-growing field. For example, for effective knowledge discovery in information networks, integrated clustering and ranking may lead to the discovery of high-quality clusters and object ranks in large networks. Mining knowledge in multidimensional space. When searching for knowledge in large data sets, we can explore the data in multidimensional space. That is, we can search for interesting patterns among combinations of dimensions, attributes, at varying levels of abstraction. Such mining is known as exploratory multidimensional data mining. In many cases, data can be aggregated or viewed as a multidimensional data cube. Mining knowledge in cube space can substantially enhance the power and flexibility of data mining. Data mining, an interdisciplinary effort. The power of data mining can be substantially enhanced by integrating new methods from multiple disciplines. For example, to mine data with natural language text, it makes sense to fuse data mining methods with methods of information retrieval and natural language processing. As another example, consider the mining of software bugs in large programs. This form of mining, known as bug mining, benefits from the incorporation of software engineering knowledge into the data mining process. Boosting the power of discovery in a networked environment. Most data objects reside in a linked or interconnected environment, whether it be the web, database relations, files, or documents. Semantic links across multiple data objects can be used to advantage in data mining. Knowledge derived in one set of objects can be used to boost the discovery of knowledge in a related or semantically linked set of objects. Handling uncertainty, noise, or incompleteness of data. Data often contain noise, errors, exceptions, or uncertainty, or are incomplete. Errors and noise may confuse the data mining process, leading to the derivation of erroneous patterns. Data cleaning, data pre-processing, outlier detection and removal, and uncertainty reasoning are examples of techniques that need to be integrated with the data mining process. Pattern evaluation and pattern or constraint-guided mining. Not all the patterns generated by data mining processes are interesting. What makes a pattern interesting may vary from user to user. Therefore, techniques are needed to assess the interestingness of discovered patterns based on subjective measures. These estimate the value of patterns with respect to a given user class based on user beliefs or expectations. Moreover, by using interestingness measures or user-specified constraints to guide the discovery process, we may generate more interesting patterns and reduce the search space. User interaction. The user plays an important role in the data mining process. Interesting areas of research include how to interact with the data mining system, how to incorporate a user's background knowledge in mining, and how to visualize and comprehend data mining results. We introduce each of these here. Interactive mining. The data mining process should be highly interactive. Thus, it is important to build flexible user interfaces and an exploratory mining environment, facilitating the user's interaction with the system. A user may like to first sample a set of data, explore general characteristics of the data, and estimate potential mining results. Interactive mining should allow users to dynamically change the focus of a search, to refine mining requests based on returned results, and to drill, dice, and pivot through the data and knowledge space interactively, dynamically exploring queue space while mining. Incorporation of background knowledge. Background knowledge, constraints, rules, and other information regarding the domain under study should be incorporated into the knowledge discovery process. Such knowledge can be used for pattern evaluation as well as to guide the search toward interesting patterns. Ad hoc data mining and data mining query languages. Query languages, for example SQL, have played an important role in flexible searching because they allow users to pose ad hoc queries. Similarly, high-level data mining query languages or other high-level flexible user interfaces will give users the freedom to define ad hoc data mining tasks. This should facilitate specification of the relevant set of data for analysis, the domain knowledge, the kinds of knowledge to be mined, and the condition and constraints to be enforced on the discovered patterns. Optimization of the processing of such flexible mining requests is another promising area of study. Presentation and visualization of data mining results. How can a data mining system present data mining results vividly and flexibly so that the discovered knowledge can be easily understood and directly usable by humans? This is especially crucial if the data mining process is interactive. It requires the system to adopt expressive knowledge representations, user-friendly interfaces, and visualization techniques. Efficiency and scalability. Efficiency and scalability are always considered when comparing data mining algorithms. As data amounts continue to multiply, these two factors are especially critical. Efficiency and scalability of data mining algorithms. Data mining algorithms must be efficient and scalable in order to effectively extract information from huge amounts of data in many data repositories or in dynamic data streams. In other words, the running time of data mining algorithm must be predictable, short, and acceptable by applications. Efficiency, scalability, performance optimization, and the ability to execute in real time are key criteria that drive the development of many new data mining algorithms. Parallel, distributed, and incremental mining algorithms. The humongous size of many datasets, the wide distribution of data, and the computational complexity of some data mining methods are factors that motivate the development of parallel and distributed data-intensive mining algorithms. Such algorithms first partition the data into pieces. Each piece is processed in parallel by searching for patterns. The parallel processes may interact with one another. The patterns from each partition are eventually merged. Cloud computing and cluster computing, which use computers in a distributed and collaborative way to tackle very large-scale computational tasks, are also active research themes in parallel data mining. In addition, the high cost of some data mining processes and the incremental nature of input promote incremental data mining, which incorporates new data updates without having to mine the entire data from scratch. Such methods perform knowledge modification incrementally to amend and strengthen what was previously discovered. Diversity of database types. The wide diversity of database types brings about challenges to data mining. These include handling complex types of data. Diverse applications generate a wide spectrum of new data types, from structured data such as relational and data warehouse data to semi-structured and unstructured data, from stable data repositories to dynamic data streams, from simple data objects to temporal data, biological sequences, sensor data, spatial data, hypertext data, multimedia data, software program code, web data, and social network data. It is unrealistic to expect one data mining system to mine all kinds of data, given the diversity of data types and the different goals of data mining. Domain or application-dedicated data mining systems are being constructed for in-depth mining of specific kinds of data. The construction of effective and efficient data mining tools for diverse applications remains a challenging and active area of research. Mining dynamic, networked, and global data repositories. Multiple sources of data are connected by the Internet and various kinds of networks, forming gigantic, distributed, and heterogeneous global information systems and networks. The discovery of knowledge from different sources of structured, semi-structured, or unstructured, yet interconnected data with diverse data semantics poses great challenges to data mining. Mining such gigantic interconnected information networks may help disclose many more patterns and knowledge in heterogeneous datasets that can be discovered from a small set of isolated data repositories. Web mining, multi-source data mining, and information network mining have become challenging and fast-evolving data mining fields. Data mining and society. How does data mining impact society? What steps can data mining take to preserve the privacy of individuals? Do we use data mining in our daily lives without even knowing that we do? These questions raise the following issues. Social impacts of data mining. With data mining penetrating our everyday lives, it is important to study the impact of data mining on society. How can we use data mining technology to benefit society? How can we guard against its misuse? The improper disclosure or use of data and the potential violation of individual privacy and data protection rights are areas of concern that need to be addressed. Privacy-preserving data mining. Data mining will help scientific discovery, business management, economy recovery, and security protection. For example, the real-time discovery of intruders and cyber attacks. However, it poses a risk of disclosing an individual's personal information. Studies on privacy-preserving data publishing and data mining are ongoing. The philosophy is to observe data sensitivity and preserve people's privacy while performing successful data mining. Invisible data mining. We cannot expect everyone in society to learn and master data mining techniques. More and more systems should have data mining functions built within so that people can perform data mining or use data mining results simply by mouse clicking without any knowledge of data mining algorithms. Intelligent search engines and internet-based stores perform such invisible data mining by incorporating data mining into their components to improve their functionality and performance. This is done often unbeknownst to the user. For example, when purchasing items online, users may be unaware that the store is likely collecting data on the buying patterns of its customers, which may be used to recommend other items for purchase in future. Stress on importance of its application potential. As a highly application-driven domain, data mining has incorporated many techniques from other domains such as statistics, machine learning, pattern recognition, database and data warehouse systems, information retrieval, visualization, algorithms, high-performance computing, and many application domains. The interdisciplinary nature of data mining research and development contributes significantly to the success of data mining and its extensive applications. In this section, we give examples of several disciplines that strongly influence the development of data mining methods. Statistics. Statistics studies the collection, analysis, and interpretation or explanation and presentation of data. Data mining has an inherent connection with statistics. A statistical model is a set of mathematical functions that describe the behavior of the objects in a target class in terms of random variables and their associated probability distributions. Statistical models are widely used to model data and data classes. For example, in data mining, tasks like data characterization and classification, statistical models of target classes can be built. In other words, such statistical models can be the outcome of a data mining task. Alternatively, data mining tasks can be built on top of statistical models. For example, we can use statistics to model noise and missing data values. Then, when mining patterns in a large data set, the data mining process can use the model to help identify and handle noisy or missing values in the data. Statistics research developed tools for prediction and forecasting using data and statistical models. Statistical models can be used to summarize or describe a collection of data. Statistics is useful for mining various patterns from data as well as for understanding the underlying mechanisms generating and affecting the patterns. Inferential statistics or predictive statistics models data in a way that accounts for randomness and uncertainty in the observations and is used to draw inferences about the process or population under investigation. Statistical methods can also be used to verify data mining results. For example, after a classification or prediction model is mined, the model should be verified by statistical hypothesis testing. A statistical hypothesis test, sometimes called confirmatory data analysis, makes statistical decisions using experimental data. A result is called statistically significant if it is unlikely to have occurred by a chance. If classification or prediction model holds true, then the descriptive statistics of the model increases the soundness of the model. Applying statistical methods in data mining is far from trivial. Often, a serious challenge is how to scale up statistical method over a large data set. Many statistical methods have high complexity in computation. When such methods are applied on large data sets that are also distributed on multiple logical or physical sites, algorithms should be carefully designed and tuned to reduce the computational cost. This challenge becomes even tougher for online applications, such as online query suggestions in search engines, where data mining is required to continuously handle fast, real-time data streams. The figure shows that data mining adopts techniques from many domains. Machine learning. Machine learning investigates how computers can learn or improve their performance based on data. A main research area is for computer programs to automatically learn to recognize complex patterns and make intelligent decisions based on data. For example, a typical machine learning problem is to program a computer so that it can automatically recognize handwritten postal codes on mail after learning from a set of examples. Machine learning is a fast-growing discipline. Here we illustrate classic problems in machine learning that are highly related to data mining. Supervised learning is basically a synonym for classification. The supervision in the learning comes from the labeled examples in the training dataset. For example, in the postal code recognition problem, a set of handwritten postal codes images and their corresponding machine-readable translations are used as training examples which supervise the learning of the classification model. Unsupervised learning is essentially a synonym for clustering. The learning process is unsupervised since the input examples are not class-labeled. Typically, we may use clustering to discover classes within the data. For example, an unsupervised learning method can take as input a set of images of handwritten digits. Suppose that it finds 10 clusters of data. These clusters may correspond to the 10 distinct digits of 0 to 9 respectively. However, since the training data are not labeled, the learned model cannot tell us the semantic meaning of the clusters found. Semi-supervised learning is a class of machine learning techniques that make use of both labeled and unlabeled examples when learning a model. In one approach, labeled examples are used to learn class models, and unlabeled examples are used to refine the boundaries between classes. For our two-class problems, we can think of the set of examples belonging to one class as the positive examples and those belonging to the other class as a set of negative examples. Active learning is a machine learning approach that lets users play an active role in the learning process. An active learning approach can ask a user, such as a domain expert, to label an example which may be from a set of unlabeled examples or synthesized by the learning program. The goal is to optimize the model quality by actively acquiring knowledge from human users, given a constraint on how many examples they can be asked to label. If we do not consider the unlabeled examples, the dashed line is the decision boundary that best partitions the positive examples from the negative examples. Using the unlabeled examples, we can refine the decision boundary to the solid line. However, we can detect that the two positive examples at the top right corner, though labeled, are likely noise or outliers. Figure shows semi-supervised learning. Database systems and data warehouses. Database systems research focuses on the creation, maintenance, and use of databases for organizations and end users. Particularly, database systems researchers have established highly recognized principles in data models, query languages, query processing and optimization methods, data storage and indexing and accessing methods. Database systems are often well known for their high scalability in processing very large, relatively structured data sets. Many data mining tasks need to handle large data sets or even real-time fast streaming data. Therefore, data mining makes good use of scalable database technologies to achieve high efficiency and scalability on large data sets. Moreover, data mining tasks can be used to extend the capability of existing database systems to satisfy advanced users' sophisticated data analysis requirements. Recent database systems have built systematic data analysis capabilities on database data using data warehousing and data mining facilities. A data warehouse integrates data originating from multiple sources at various time frames. It consolidates data in multi-dimensional space to form partially materialized data cubes. The data cube model not only facilitates OLAP in multi-dimensional databases, but also promotes multi-dimensional data mining. Information retrieval. Information retrieval, IR, is a science of searching for documents or information in documents. Documents can be text or multimedia and may reside on the web. The differences between traditional information retrieval and database systems are twofold. Information retrieval assumes that data under search are unstructured, and the queries are formed mainly by keywords which do not have complex structures, unlike SQL queries in database systems. The typical approaches in information retrieval adopt probabilistic models. For example, a text document can be regarded as a bag of words, that is, a multi-set of words appearing in the document. The document's language model is the probability density function that generates the bag of words in the document. The similarity between two documents can be measured by the similarity between their corresponding language models. Furthermore, a topic in a set of text documents can be modeled as a probability distribution over the vocabulary, which is called a topic model. A text document which may involve one or multiple topics can be regarded as a mixture of multiple topic models. By integrating information retrieval models and data mining techniques, we can find the major topics in a collection of documents, and for each document in a collection, the major topics involved. Increasingly large amounts of text and multimedia data have been accumulated and made available online due to the fast growth of the web and applications such as digital libraries, digital governments, and healthcare information systems. Their effective search and analysis have raised many challenging issues in data mining. Therefore, text mining or multimedia data mining, integrated with information retrieval methods, have become increasingly important. Conclusion. In this chapter, we have covered the following in detail: an introduction to multidisciplinary field of data mining, discussion on the evolutionary path of database technology that has led to the need for data warehousing and data mining, different kind of data on which data mining is applied, classification of data mining system, major issues in data mining, stress on importance of its application potential.